Hey, welcome back. This is problem 2, which is from the 2017 AMC 10A, problem number 17. This is a nice number theory problem. There are 10 horses named creatively horse 1, horse 2, and all the way to horse 10. They get their names from how many minutes it takes for them to run one lap around a circular racetrack. Horse K runs one lap in exactly K minutes. At time 0, all the horses are together at the starting point on the track. The horses start running in the same direction and they keep running around the circular track at their constant speeds. The least time s greater than 0 in minutes at which all 10 horses will again simultaneously be at the starting point is s equals 2520. Let t greater than 0 be the least time in minutes such that at least 5 of the horses are again at the starting point. What is the sum of the digits of t? To solve this problem, we need to think about which 5 horses we can pick in this case. If we can just draw some examples, maybe we can get an idea. In this case, let's consider the which horses are at each time step. So, for example, where are they at time 0? Which horses are at the starting point, right? We know that at the start, if we represent the horse numbers here and the time on this side, then at time 0, well, all of the horses are at the starting point. However, as we progress, for example, at time 1, only horse 1 is at the starting point. We know that horse 1 will automatically be at the starting point for all times, 1, 2, 3, 4, 5, and so on. 2 will be at every multiple of 2, right? 3 will be at every multiple of 3. So we can see that the number of horses at any point, for example, for any multiple of 6, we know that horses 1, 2, and 3 are automatically going to be at the starting point, right? So we actually expect our number, maybe counterintuitively, to actually be really small because there exist some nice small numbers where all of these horses will be at the starting point. And we can see that 3 is already almost there. We just need to find actually at 6, right? 1, 2, 3, and 6 will be at the starting point if we look at all of the possibilities, right? So we can see that in this case, 6 is almost there. We just need to find some number that is slightly greater in order to reach 5. One way to proceed is to simply just use brute force, right? And just find the smallest value, which actually won't take too much time. However, maybe we can think about this in a more, smart way, which in this case just means thinking about factors, right? In this case, we know that if 4, for example, is a divisor of the time, then so is 2. So 4 actually implies, if 4 is at the starting point, then so is 2. In a similar vein, if 8 is at the starting point, then so is 4, right? And actually we can construct this sort of graph or this sort of diagram indicating, for example, 6, if 6 is, then so is 2. If 6 is, then so is 3, right? And we can actually think about it in that sense, right? So we can see that 1 obviously will be at the start at every t. So then we can clearly see this. As we progress, we can see in this diagram, for example, there's already more than 5 or 5. There's already 6 numbers here. So for example, if we can confirm that a number is divisible by both 8 and 6, then we're also divisible by 1, 2, 3, and 4, which that is at least 5 horses. In fact, it's 6. Similarly, if a number is divisible by both 4 and 6, then we're also happy, right? In particular, 1, 2, 3, 4, and 6. So actually from this, we can see that, well, any number that's divisible by 4 or 6, or the LCM of 4 and 6, or any multiple thereof, in this case 12, would actually work as t. In fact, we know that at time t equals 12, 1, 2, 3, 4, and 6 will be at the starting point, which indicates that 12 is an upper bound on our possible time. There could be a smaller number, but we can just quickly verify that every number less than 12 will not work. For example, 7 only has divisors 1 and 7, so only 2. 8 has 4, 1, 2, 3, 1, 2, 4, and 8. 9 has 3, 1, 3, and 9. 10 has 1, 2, 5, and 10. And finally, 11 has just 1, right? So in this case, we know that indeed 12 is the smallest possible value of t, which gives us an answer of 3, B.